Okay, good morning, everyone. Hope you're all well. Um, just a couple of housekeeping notes. You're working your way through deliverable 9, and we'll talk about the 10th and final deliverable next Tuesday. Any questions about deliverable 9? So far, so good? Okay, so back to our discussion about looking outward and stitching ubiquitous technology out into the world. We're working our way through a three-part lecture on applying ubiquitous technology to different applications. In 17 and 19, we're looking at two different scientific projects and using ubiquitous technology to try and tackle scientific questions that would be difficult or impossible to answer without that kind of technology. And we're going to spend most of our time on lecture 18 this morning on human activity recognition, where the application here is self-health monitoring. Okay. So part of looking at human activity monitoring is to try and determine what activity the human is performing and in what context. So another term for this is context-aware system, which takes us back to our PACT analysis. If an interactive technology wants to notify the user of some event, is it an appropriate time to do so? How does the technology infer the context surrounding the user at that time? Okay, we looked at Fitbit. There's a lot of obviously commercial applications of this now, various aspects of physical and mental well-being. Some of these dimensions of physical and mental well-being are easier to quantify than others. We looked at some emerging technologies to actually measure automatically what and how much you eat per day, kind of an interesting technology. We started to unpack, when we ended last time, we were unpacking this table which delineates the various dimensions or features of trying to automatically recognize human activity with sensors. As usual, we need to think about what are the different ways in which that activity can differ and how does that inform how we go about deploying sensors to try and detect that activity. We looked at offline and online execution last time. Is the system trying to recognize the activity as the user is performing the activity or only after the fact? We looked at trying to predict what the user is doing based on data that is drawn from a large number of users and used to train a common machine learning algorithm. Or are we going to try and tailor or create a specific machine learning algorithm? Are we going to try and fit data from just individual users and come up with a model just for them? We need to think very carefully about the temporal aspects or how the activity unfolds over time. There are additional issues if we're using sensors, because since sensors themselves change over time, they degrade or they need to be reset. Then we focused on recognition itself. Are we recognizing continuously over the course of time, or are we trying to look at isolating particular activities that occur during particular periods of time, which requires the sensor, the machine learning algorithm, to segment or break up sensor data that is coming in over time into distinct segments. Your Leap Motion device does this for you already. You don't need to do any segmentation. But if you're getting a continuous flow of data, it depends. It's important to try and figure out where the beginning and end should be of the recognition event. And this is particularly true with activities that oscillate over time. If, for example, the activity might be biking or running, you have a repeated movement that is repeating over a second or two, so it's a relatively high frequency, so we want a relatively short series of segments. But if we're trying to recognize whether somebody is playing a sport or playing an instrument, that session may occur over a longer period, and the repetition in a game of tennis, for example, or playing an instrument, playing a song, the frequency of something that repeats might be over the course of minutes rather than seconds. So if we manually set the segment to be too narrow, we might miss the oscillation because the oscillation goes outside of this segment of time. Or if the window is too wide, we might capture a little bit of running and then a little bit of biking and not be sure what activity it is. So we might call in an oracle, and an oracle is a term from machine learning, meaning sort of a human expert who is able to reach in and help the machine learning algorithm in some way. So the oracle is someone who might say, okay, between 8 and 9 a.m. on the user's Fitbit or accelerometer, you should set the segment to be less than a minute because they tend to exercise in the morning, and you'll be able to capture those high frequency oscillations then. But in the afternoon, they're performing some other activity like tennis or playing an instrument, and which of those activities they're performing, you might need a larger window. The oracle is dictating how to segment the data. Okay, as I just mentioned, obviously we're trying to recognize human activities, many of which are periodic. Mentions here sliding window segmentation. So once we know the size of the window, we might try and recognize what activity is being performed during that time period, and then slide the window forward, ask what activity is being performed during that period, slide the window forward, and so on. Usually we're looking for in that segment we're looking for frequency domain features. What does frequency domain mean? Well, typically if you're looking at a graph where on the horizontal axis you have time, the vertical signal is giving you the strength of some signal. So for example, if we're recording information from an accelerometer, which is telling us something about acceleration, then the vertical axis is positive acceleration, and lower on the vertical axis is negative acceleration, and you have 0 in the middle. In time domain, in frequency domain, that's time domain, time on the horizontal axis. In frequency domain, you have frequencies on the horizontal axis, and you might also have a curved line where now the vertical height represents the strength of a given frequency. So as we move from low frequency on the left side of the graph to high frequency on the right side of the graph, and you look at the bumps and valleys along there, it's going to tell you in a given signal how much the strength of the frequency. So let's look at an example. Let's imagine someone is wearing an accelerometer and they're riding a bicycle. So assuming that accelerometer is on their leg, so you're capturing the cycles on the bike, those cycles are going to be, depending on how fast they're riding, let's say it's 1 second. So every second they repeat a cycle on the bicycle. If you look at the time domain plot of this, if you go along to a frequency of 1 second, you'll see a strong signal that represents that in that data that's coming from the accelerometer, the frequency domain calculation is telling you there's a strong oscillation at 1 second. Let's imagine that someone is biking, trying to think of an example here. Let's say they're biking on a what's it called? A velocodrome, a track that's made for a bicycle, and unlike a running track, it's rotated upwards so someone can bike around that biking track very quickly. As they go around the track, maybe it takes them 30 seconds to go around that track. The accelerometer is going to measure certain oscillations as they repeat around the track. So maybe they start up and slow down at certain points on the track, and that speeding up and slowing down on the track repeats at about a 30-second oscillation. That means there are 2 oscillatory signals going on in that's being recorded by the accelerometer. There's the fast 1 second frequency of cycling on the bike, and the slower 30-second frequency of their acceleration and slight deceleration around the track. So if we go back to the frequency domain and we go across to 1 second, we see a spike at that point. If we go further to the right on that plot to the 30-second point, we'll see another maybe less tall peak. So in this frequency domain plot, we have 2 mountains, 2 peaks, one at 1 second and one at 30 seconds. So imagine those are features, those time domain features, the bumps and the bumps and valleys in that frequency domain plot. Imagine those become features that we feed into a machine learning algorithm. and it's trying to classify what activity the subject is currently carrying out. Are they biking outside? Are they biking indoors on a track? Are they running? Are they walking? And so on. Frequency domain features make sense because for a lot of activities, there are oscillations and there are combinations of faster and slower oscillations. Okay. Alternatively, the activity might not be periodic, or it may be periodic but sporadic. Maybe somebody walks for a short period of time and then sits down in a park and then walks again, meets a friend and stops to chat, walks again. How do we capture particular activities that are appearing sporadically throughout the user's day? Again, segmentation is going to be important. If we have too large a segment, if we're averaging or looking for features within that large segment of time, short spikes of a particular activity that we're interested in are going to be blurred out by the other things that the user is doing within that interval of time. And again, too short a segment, we might capture that sporadic event. Actually, sorry, we want a small period of time in order to capture those sporadic events. Okay. The activity may not be periodic, it may not be sporadic, it may be static. So in your Leap Motion application, obviously you're dealing with static poses. You ask the user to sign a sign and then hold that pose. Alternatively, you can also consider this activity sporadic because they're doing 0 and then they're doing 1 and then they're going back to 0. Luckily, you are driving the activity through the interface, so the segmentation is easy. You know when to look for whether the user is signing 0 because you know when you started to ask them to sign 0 and you know when you stopped asking them to sign 0. Okay. If we have this sensor data, what other information might we need? So if we want to go stateless, meaning we're going to ignore the state of the world. Stateless here means state of the world. Doesn't matter what else is going on in the user's environment. We are assuming that we can infer what the user is doing directly from sensor data without having to know the context of the external world. For the moment, this is the dominant approach in human activity recognition systems, simply because it's easier. Okay. Some activities, however, it might be useful to know something about the environment that the user is currently in. So, where is the user, for example? Can you localize them with GPS on a map? Are there locations of objects nearby that might provide hints about what the user is doing? If you could determine these additional features, it might make it easier on your machine learning algorithm to detect or infer what activity the user is carrying out. But of course, so this might make things easier, but it comes at a cost in that we need more sensors and we need to try and draw in more information. What might be some human activities that would be easier to infer if you had additional information beyond the sensors that the user is wearing? Let's imagine that the user has an accelerometer. Your smartphone has an accelerometer in it, so assuming that's turned on, if you have the motion of a user that is carrying their phone with them, what are some activities that might be difficult to infer just from accelerometer data, where it might be easier if you know where they are, what other objects are nearby, what other people are nearby, and so on? What kinds of activities might it be useful to take a stateful approach to inferring activity? If you have an idea, go ahead and type it into chat. What activities might it be easier to infer if you know where, if you had GPS data? So as David says, biking is difficult if you're using the accelerometer in the phone because unless you have a phone in a thigh pocket, You're not going to get information about the legs. So you might get distance. So as Sarah says, we could, if we got GPS information, we could look at displacement. We could infer displacement from GPS. How far did they move? If we know how far they moved in a unit time, we might be able to distinguish between, as Sarah says here, walking, running, and biking. If somebody moves a fair distance in a short period of time, it's probably unlikely that they're walking. They're either running and biking. You might be able to get a little bit of frequency information from the accelerometer in the phone that might help you distinguish between walking and biking. Although distinguishing between running and biking is difficult, because for most people, again, depending on how quickly you're biking, the frequency of oscillation in pedaling is pretty close to an oscillation for a steady jog. You can probably see from this example that distinguishing between certain pairs of activities can be difficult given just one sensor modality, one type of sensor like accelerometer. So in most human activity recognition systems, we try and bring in information from multiple sensors to help the machine learning algorithm distinguish between these similar activities. Okay, let's have a look at another table here. We're not going to go through this entire table, but this is an interesting table you can find from the paper that I've linked for today. This lists most of the common sensors that are used in human activity recognition systems. A lot of these exist in your smartphone, and with not a lot of effort, you could probably write an app for your phone that makes use of these sensors, pushes that sensor data through a KNN, for example, which most of you are familiar with at this point, and do a pretty good job of predicting some of your own activities. Okay, so in this table here, as we're going to see in a moment, they're going to list a whole bunch of different kinds of sensors. And then where are these sensors located? Are they in the environment? Are they located in objects, or are they being worn on the subject's body? We're then going to think about, for that particular sensor, what kinds of applications and what kind of activities might be detected by that sensor. So a microphone, obviously, there could be a microphone out there in the environment, assuming it's turned on. It might be a microphone that's embedded in another object, like a laptop that someone is using. Or it might be something that's worn on the body. So if we assume the microphone is embedded in an object, which is the smartphone, and you're wearing your smartphone or you're carrying it in a pocket, then that particular microphone is both O and B. What kinds of activities can be inferred from data arriving from a microphone? Let's assume that we're thinking about the microphone that's turned on your smartphone that you're wearing while you go about your day. What kinds of activities might microphone data provide a hint about? We actually saw a couple of examples one lecture back. We saw in the previous lecture the example of a microphone that was inferring a particular activity, which is having a conversation, right? Is the user currently speaking? Is there the sound of someone else speaking? And are those two sound sources, high volume and medium volume, alternating? And if they are, you might be able to, as Bryce says, infer that there's a conversation going on between two people. Assuming you can actually infer the ID or the identity of the person from the microphone data, you might be able to figure out who is speaking to whom and might actually start to determine friendships and start to build up the social network of the person wearing the microphone. Again, that's a very invasive application. David mentions that Bluetooth is even better for determining social interaction networks How so, David? How is Bluetooth useful here? What else other than, while David is thinking about that, what else other than voices and conversations what other activities might a microphone provide hints about? Think about all the activities you take part in throughout the day. Assuming that it's recorded by those activities are recorded by a microphone. Okay, so locating the position of two Bluetooth devices and working those back to people. Yeah, absolutely. Population in an area. That's a great example, Sarah. So in the before times when people tended to congregate together physically, you might be able to guess whether the person is in a crowd, how populous is their immediate environment. That might give you a hint about what activity they're engaged in. If the smartphone is in the user's pocket, then obviously the microphone is going to be muffled somewhat. But assuming that the microphone can capture enough, that the microphone is unmuffled, it might also give you a lot of information about lots of other physical activities. What are the sounds that your legs make as you bike or run or walk or skateboard or take the bus? A lot of information from an audio feed. Okay, here's a long list of other kinds of sensors. Some of these are embedded in your phone, some are not. I'm just going to pick out a few that are important here. Inertial measurement units, these are important because they give information about orientation. What is the orientation of the body? Accelerometers in your phone give information about movement, which is obviously useful for things like biking and walking and things that repeat over time. But if we're interested in static poses, then an inertial measurement unit can be useful because it gives information about orientation or static poses. Is the user sitting for a long period of time, standing for a long period of time, leaning at an odd angle for a long period of time? These all give hints about the current activities that the user is engaged in. Some of these sensors are very invasive, like a capacitative sensing, so breathing and fluid intake. These are like these sensors we looked at before that are inside the mouth. Sensors that give information about skin temperature, galvanic skin response. So skin conductivity, the amount of sweat or moisture on the skin increases or decreases flow of electricity, and moisture on the skin gives a lot of information about emotional state, level of arousal, anxiety levels, and so on. But again, it's pretty invasive. This is a patch or something that you need to wear literally on the skin. I've singled out a pressure sensor here. This is pressure, air pressure. Assuming you had an air pressure sensor that you're wearing throughout the day, what information does that provide? Well, it gives information about air pressure. What activities correlate with air pressure? Seems like kind of an odd one. Absolutely. So climbing stairs indoors, or as Sarah says, elevation for out of doors. So pressure is useful for vertical motion. Swimming, assuming you're gonna wear it when you're swimming, or you leave your smartphone on deck while you go swim in the pool. A lot of information you might be able to pull out of a pressure sensor. Here's another interesting one. Which is electrooculography. We've talked already about EMG and EEG when we talked about the Libet experiment that provided evidence, seemingly, against free will. We saw an EMG sensor that was wrapped around the subject's finger, which gives information about muscle contraction. So EMG from myo or muscle. EEG, electroencephalography, is something you need to wear on the skin, on the skull, and gives information about electrical activity on the surface of the brain. Again, very invasive, not very acceptable. Most of us aren't going to walk around with helmets or patches on our scalp. Electrocardiography, assuming you wear a belt near your chest, this will give you information about heart rate. Electrooculography is a sensor that gives information about eye direction. Assuming that someone was willing to wear sensors, there's small patches that would normally be on the side of the skull, and they're able to detect muscle contractions or skin contractions near the eye, which are features that can predict where the eye is looking. What kinds of activities might you infer if all you had available was an EOG signal over time? Again, think about your daily routine, all the various activities you engage in. Assume you were able to get a raw sensor feed of how your eyes were moving about in your head throughout the day. What activities might you be able to infer from that? This one's a little trickier. Any ideas? So driving and reading, yeah, absolutely. So if you watch somebody driving, next time you're in the car with someone, watch their eyes and look at where they're looking. How often do they change the direction of their gaze? What's the total angle of their gaze that's changing? And again, watch somebody reading and pay careful attention to their eye, the change in their eye direction. You can imagine those two different signals, those two different EOG signals coming from driving and reading. They're probably going to be pretty difficult. Turns out you can actually infer quite a bit about not just reading, but other cognitive processes. Is someone doing a math problem? Is somebody building, doing arts and crafts with their hands? A lot of things that require mental effort. You can get quite a bit from EOG. I've linked in here, this is an older study from 2011. Here are some EOG sensors, again, pretty invasive. In this study, the subject was instrumented with EOG and then shown a series of images, one after the other. A random half of those images had been seen by the user before, and the other half of the images had not been seen by the user before. And it turns out that a machine learning algorithm with just EOG data could predict whether the subject had seen that picture before based on the way they looked at that picture, how their eyes saccaded around the image. Kind of interesting. If Google Glass or some other eye-based ubiquitous technology returns, if there's a camera that's not just looking outward, but looking inward from the glasses at the eyes, might be possible to infer quite a bit about what the user is doing and provide some interface or some scaffolding to help them with that process. Okay, so we're now going to, one other thing I wanted to talk about is this arc of going from raw sensor data to activity inference, trying to predict exactly what activity the user is engaged in. There's a very recent paper from last year, 2019. I've linked to that paper, which discusses how to use deep learning to infer activities. And in that paper, they distinguish between ways of doing this without deep learning and with deep learning. So I thought this was an interesting way to contrast what the benefit of deep learning is over other machine learning algorithms. Again, this is not a machine learning class, but especially in activity recognition, it turns out that deep learning is particularly useful for the following reason. Again, we are assuming in activity recognition that we are collecting multimodal sensor data, multimodal. So meaning that we are collecting data from lots of different sensor modalities, different kinds of sensors. Usually we need to take that raw data and do feature extraction. So if we go back to the Leap Motion example, the Leap Motion device itself collects raw infrared data and then congeals or condenses that raw data down into a smaller set of numbers, which become features for your KNN. How to compress that raw data down into useful features is known as feature extraction, and this is a difficult step in machine learning. Luckily, in your Leap Motion application, this difficult step has been performed for you. So if we get all this raw data, do we take the minimum value in the data, the maximum value, the range? Do we look at the data in the time domain? How is acceleration changing over time? Or do we look at particular data in the frequency domain? Do we look at acceleration data and ask, what is the strength of various oscillations at different frequencies in that signal? That requires a lot of human intuition and a lot of human bias. We need to have an assumption about which of these features is going to be most helpful in predicting activities like going upstairs, downstairs, running, riding a bike, and so on. Once you have figured out how to turn this raw data into features, so again, Leap Motion going from raw infrared data to triplets of XYZ positions, the positions of the bones in the hand, then you need to pick a machine learning algorithm, train that machine learning algorithm on those features, and train it to predict or classify which of a set of activities the user is currently engaged in. One of the many benefits of the machine learning revolution, or the deep learning machine learning algorithm, is it does away with this second step. We no longer need to do feature extraction. So here are 4 different kinds of deep networks. They don't matter for our purposes. But the basic idea here is that we're going to take raw data, feed it into one side of the network, and the other side of the network is going to output a classification label. It's going to output a prediction about what activity the user is carrying out. So this would be like taking the raw infrared data directly from the Leap Motion device and training a deep network to predict which of the 10 ASL digits the user is currently signing. We can skip over this step of inferring positions of the bones in the hand from raw infrared data. Okay, for those of you that are interested in machine learning and deep learning, you can go and have a look at this paper that discusses deep learning applications to human activity recognition. Okay, we're going to go back to this older paper from 2014 where they did an actual study. They placed 3 different accelerometers, like you see here, on 2 different subjects. They had 2 human subjects in this case. And these 2 subjects, over a period of time, performed the following 12 activities: opening and closing a window, watering a plant, turning book pages, and so on. These 11 activities. And then a 12th activity called null, which is the user was just asked to basically stay still, just hang out, sit in a chair, read something, but don't read something on the screen or with a book, but try not to move your arm too much. For better, for worse, most of us, for the majority of our day, we are stationary. So we need to know, if we're going to try and train sensor data or acceleration data from an accelerometer of which of these activities we're performing, it's which of these activities relative to a baseline, which is not much movement at all. Assuming that you have this acceleration data from these 2 different human subjects, both of them performed these different activities, which pair of activities here do you think it's going to be most difficult for the machine learning algorithm to distinguish between? So put another way, which pair of activities here are going to have the most similar acceleration data? So as you can see from the cartoon here, we're getting three dimensions of acceleration. I'll just do the wrist for a moment. So we have X, Y, and Z. So for each of those 3 axes, we can ask how quickly I'm accelerating in one direction or how much I'm accelerating in the other direction as a floating point value. So you have basically over time, you have 9 signals, the 3 accelerations at the wrist, the forearm, and the upper arm. Given those nine time series data sets, if you looked at pairs of these 9 signals, which pair of 9 signals are going to be most similar for these activities? Which pair among these 12 activities do you think are going to be most similar to one another? No guesses? Okay, we're going to actually look at this study. We'll see which one is more difficult than which other one. Again, we're gonna look at this machine learning pipeline here, where, like I just said, we're going to start with raw data. In this particular experiment, for the moment, we're just going to look at acceleration from the wrist. So we're going to discard the acceleration from the upper arm and the lower arm. So we just have three sets of sensor data. The experimenters, which in this case are the oracles, they have picked a 1-second sliding window. They're assuming that given 1 second of acceleration data and sliding that window over these 1-second windows, that's going to give a bunch of signals. In each of those 1-second time windows, they're going to calculate 2 numbers. What is the mean acceleration for X, Y, and Z in that 1-second time period? And what is the variance? What is the variability in the acceleration, the X acceleration, Y acceleration, and Z acceleration within that window? And then if they slide the window 18 times, they're going to get 18 pairs of numbers, which give a total of 36 features. So they're doing feature extraction here. They're not using deep learning in this experiment. They're feeding those 36 features into nearest class centroid, or NCC, which, as you can probably guess from the name, is very, very close to the KNN algorithm. What's the difference between NCC and KNN? Again, you can probably guess from the name. How does the NCC algorithm predict the class of a new set of 36 features? So if we have our training data, we have training data that we've collected from all of these 12 activities performed by these 2 users. So we have 12 classes. Remember, in the IRIS data set, you had 4 classes. In your Leap Motion device application, you have 10 classes. In this case, they have 12 classes. For each of these 12 classes, you take in this 36-dimensional space, because we have 36 features, you find all the points that correspond to opening a window, and you compute the average position, or the average value of the 36 features corresponding to opening a window. That's the centroid. So you're going to get back 12 centroids in this 36-dimensional space, corresponding to the average set of 36 features for these 12 activities. So far, so good. If you get some new accelerometer data and distill it out into these 36 features, you can place a point in that 36-dimensional space, and whichever centroid is closest to that point, that's the predicted class label, right? Very, very similar to KNN. So the classification here, we'll ignore the math for the moment, but basically, as you know, the NCC is going to give back, in this case, an integer between 0 and 11, which is its guess of which of these 12 activities is represented by that set of 36 features. Okay. All right, so in this case, however, like I mentioned, if you think about context, most of us spend most of our time relatively stationary, and we may intermittently perform or sporadically perform some of these activities, but most of the time we're doing nothing. which means a good thing for a machine learning algorithm to do if it wants to do well is to always guess null. So we have an unbalanced data set here. This is not something we've talked about before. What happens if the activities you're trying to predict are unbalanced? Again, it's sort of a trivial thing. You don't actually even need NCC. So how do we deal with a machine learning algorithm where how do you deal with an unbalanced data set? We need to come up with a way of measuring the performance of our machine learning algorithm that takes into account the unbalancedness of the data set. So we need to come up with some way of measuring performance which would give a low score to a machine learning algorithm that does something like this. There are many ways to do this. One way to do this, and this is an idea that comes from statistics, is to compute not just one performance metric for a machine learning algorithm, but two metrics, two numbers. We're going to assign, as a machine learning algorithm is training on the training set and making predictions, we're going to, when we're providing it with test data, once it's been trained, once the NCC has been trained and put out into the world, we can ask how well does it do at predicting new activities that it's never seen before. Predicting new test data that it's never seen before. We can compute two numbers to tell us how well that algorithm is doing: precision and recall. So let's take our cheater here, our machine learning algorithm that always predicts null. If we have a whole bunch of nulls most of the time the user is sitting quietly, that machine learning algorithm is going to score a large number of true positives. So we're now going to talk about true positives, false positives, true negatives, and false negatives. This is always hard to hold in your head because we've got these double negatives. So a true positive means the activity the user is currently carrying out, let's assume it's null, the machine learning algorithm correctly predicts that it's null. It's a true positive. It got the answer right. A false positive would be if somebody is doing something other than null. So they're chopping with a knife, for example. But since our machine learning algorithm always predicts null, it gets a false positive. It says it's null. It predicts null when the actual activity is not null. Okay. If most of the data coming in after the machine learning algorithm is predicted is null, then this value is actually going to be pretty high. It's going to get quite a bit of true positives. It's going to get a lot of the nulls correct because it's always guessing nulls, but it's going to get a few of the nulls wrong because it's going to get some of the activities wrong because it's always predicting null. So this value is not going to be it's not going to be 1 because the denominator is going to be a little larger than the numerator. If we flip this around and assume that it's also trying to predict chopping a knife, it's going to get a value of let me back up a moment. It's predicting null all the time, so it's getting a value close to 1 but not quite 1. So we could make an improvement to this algorithm. So this is not getting a perfect score anymore, right? It's getting some false positives, predicting null when the activity is something other than null, chopping a knife or tennis forehand. So imagine another machine learning algorithm that goes to the other extreme, which rarely predicts null just once, or very, very rarely. And luckily, it predicts null when the activity is actually null. So it's very conservative. It tends to predict nothing, and then when the activity is actually null, it predicts null. It would get a true positive in this case, and no false positives. Whatever else the user is doing, it does not predict null, so there's no false positives. If we're just focusing on predictions about null, this particular machine learning algorithm that predicts nothing, then predicts null on one of the nulls, next time when the user is actually doing nothing, is null, does not predict something else, it's never getting a false positive. It never predicts null when the activity is not null. that machine learning algorithm would get a precision of 1.0. It seems like it's doing well, even when it's not. It's missing some cases. So what are the cases that it's missing? It's missing these false negatives. So there are cases when the user actually is performing null, and the machine learning algorithm does not predict null, so it gets a false negative. It should have predicted null, and it didn't. So usually in a machine learning algorithm, or sometimes in a machine learning algorithm, what we're looking at is trying to train a machine learning algorithm that gets a high value of precision and a high value of recall. We want it to predict the activity when it is the activity and not predict that activity when it is not that activity. Okay, so let me just back up for a moment. Here's some of the data. Remember that we have these two human subjects. In this case, they did person-dependent machine learning. So they're going to train an NCC algorithm, one for your subject one, and another NCC algorithm for the other subject. They then took those two NCCs and let them make predictions for both of the human subjects as they continued on with these 12 activities. So in the testing phase, we want to see how well they did. And they computed the precision and recall for both of the NCCs. Precision is plotted here by the medium gray bar. They mentioned red and green bars in the paper. I think that was a misprint. So in this case, the person-dependent NCCs, the machine learning algorithms that each one was trained on just that user's data, got a precision of 76.2 using just the wrist accelerometer. They went back and did this again. They did this whole arc again, where they now use data from all three of the acceleration sensors. And that was able to increase precision to 94.1. So 94.1, close to 100, means we're getting a lot of true positives, not a lot of false positives. But remember, precision doesn't tell us anything about false negatives. This algorithm, this NCC could be getting a lot of false negatives. There could be cases of a given activity where it does not predict that activity correctly. So in the second bar here, this is still the same NCC, and we can see that with the single wrist sensor, those person-dependent NCCs were getting a precision of 76.2 and a poor recall. They weren't doing very well, meaning there were a lot of false negatives. When there was a given activity, it was predicting something else. Okay. However, recall was increased when they used all three sensors. They repeated the experiment again, but now they did person-independent machine learning. So they took the acceleration data from both human subjects, combined it, and trained a single NCC on the data coming from both subjects. And as you probably noticed in your deliverables, precision and recall dropped. It's harder for the NCC to predict correctly when it's predicting acceleration data coming from different subjects. Okay, let's have a look at these activities for a moment. I haven't told you much about these two human subjects. What dimensions of human difference are likely to be causing this problem, making it harder for the machine learning algorithm to predict data coming from two subjects rather than just one? In the case of your Leap Motion device, you know what the problems were for person-independent training, which is hand size, gender, lefties and righties, and so on. What are the dimensions of human difference that matter for these activities? Any ideas? You'll notice that 3 of the 12 activities here have to do with cooking, cutting with a knife, chopping with a knife, stirring in a bowl. Think about a master chef versus someone who's not very good at cooking. Turns out that if you look at very good chefs, they all tend to cut and chop and stir in a similar way. There are good ways or efficient ways to cut and chop and stir. So, but if you look at a whole bunch of novices carrying out these tasks, the diversity in acceleration, if you were to look at the actual movements of the hand of kitchen novices, there will be much more diversity among the novices than there will be among the experts. So many of the activities here indirectly have something to do with expertise. So here's a tennis down here, tennis forehand, tennis backhand, and overhead smash. Are these 2 human subjects, is one a novice, one is a good tennis player, one's never played tennis before? Are they both experts? Are they both novices? You can imagine that there are a lot of dimensions of human difference here that are going to make things easier or harder. Okay, last thing we're going to look at in lecture 18 here, this is what's known as a confusion matrix. And a confusion matrix can also be confusing, or the first time you've seen it. I'm going to walk you through this. We have our 12 activities listed in the columns here, and the column label is ground truth, meaning these are the actual activities that the subject was carrying out over a 10-20 second period. Doesn't really matter for our purposes. The columns, on the other hand, these are the predictions of the NCC. The numbers in each cell represent the number of testing instances they had. So how many sets of 36 features was the machine learning algorithm trying to predict? So you can see there's quite a bit here. Most of the time, so if we sum up all of the numbers in this row here, these were all the instances in which the user was not doing much of anything. So what is that? Something around 30,000 instances of doing nothing. If you sum up all the numbers in opening a window, there were close to 5,000 instances of this time window in which the subject was opening a window, drinking, and so on. What do the numbers along the diagonal represent? The correct prediction, exactly, right? So in over 24,000 cases, that testing instance represented null, and the machine learning algorithm predicted null. If you look at the off diagonals, for example, this one here, this means that there were 3,200 cases in which the user was not doing much of anything, and the NCC thought that the user was watering a plant. Okay. I asked you previously which pair of activities was hardest for the machine learning algorithm to distinguish between. The confusion matrix tells you that. Which one is it? Which pair of activities was most difficult for this machine learning algorithm to distinguish between? And how do you know? Another way to think about this is if you flip this around in your head, what would you expect if there were two activities in which the machine learning algorithm was able to perfectly distinguish between? Meaning, whenever there was one activity, it always got it right, and whenever there was the other activity, it always got it right. It never confused activity A for B, and never confused activity B for A. So as Henry mentions, the hardest thing for this machine learning algorithm to distinguish between was a tennis forehand and a tennis smash. Any tennis players here? You'll notice that almost the majority of instances, not quite, there was actually slightly more for null, but there were a lot of instances here in which the user was actually performing an overhead tennis smash, and the machine learning algorithm thought that the subject was actually performing a tennis forehand. Okay. Interestingly, however, the converse is not true. So when the subject was performing a forehand, which corresponds to this row here, in only 3 of the cases, a very small number, did the machine learning algorithm actually think that this was an overhead smash. Kind of interesting here. What can you tell me about the left-hand column here? There's a lot of numbers in the left-hand column. Why? What is that telling you about this machine learning algorithm? How good or how poorly it is, or how it's performing? So this tells you that when the subject was in this column here, for the 11 non-null activities, a lot of the time the machine learning algorithm was predicting null. Why? Any ideas? We talked about this earlier, right? There tends to be a lot of null information here. So again, there's a tendency in the machine learning algorithm, even with precision and recall, to basically bias its guesses. If it's not sure, if the machine learning algorithm is not quite sure what the answer is, maybe there are several centroids that are closest to the current testing instance. Safest thing to do is guess the usual outcome, which is null. Okay, here's another last interesting one we'll look at here. A lot of the time when the user was doing null, not doing much at all, a lot of the time the machine learning algorithm was predicting watering a plant. Why? As usual, in everything to do with HCI, it's usually something to do with context. Why is null and watering a plant often confused by the machine learning algorithm here? It's probably not surprising that when the user is not doing very much, the machine learning algorithm rarely predicts an energetic task like forehand, backhand, or smash. There isn't, as Nolan says, there isn't really any distinct motion. There isn't much of an oscillation in watering a plant, at least not that I know of. That's probably part of it. It's also not a very energetic task, right? If you're watering the plant, your hand is not accelerating very quickly like it is in forehand, backhand, and smash. So low energetic low acceleration tasks like sitting and doing nothing or watering a plant makes sense. But turning the pages of a book also seems like a pretty low energetic task. And yet the machine learning algorithm does not have a problem distinguishing between null and turning the pages in a book. Why do you think that's the case? So it kind of makes sense that it has a hard time to distinguish between null and watering a plant. Why does it not have a problem between distinguishing null and turning the pages of a book? This one's trickier. Got to really think about context here. You have to think about sensors and think about, you need to think about context and the sensors. You've got these sensors on the upper arm, lower arm, and wrist. Which arm are the sensors on? While the water is pouring, you don't move your arm very much. Which arm? If you think about it, watering a plant, at least for most of us, it's a one-arm task. What if the person is watering with the off arm, the arm that does not have the sensors on it? That's going to be tricky. For most of us, turning the pages of a book is a two-hand task. So there's probably more acceleration data that you're getting from turning the pages of a book, given this sensor instrumentation, than there is from watering a plant. I don't know whether the sensors were on the arm of the subjects while they were watering the plant, but given this high air, I'm guessing it wasn't. Okay, again, a subtle detail, but this is again very important for HCI, and particularly when we're thinking about trying to infer activity from sensors that are capturing some information about the motion of the body, but not all of it. Maybe someone has strapped on their smartphone while they're exercising. Does it matter what arm the sensor is on? Maybe we want microphone data, but the smartphone is in the pocket of the subject. Is the pocket far enough down the leg of the subject that we can get oscillations from walking and biking, or do they have it in a chest pocket? Okay, lots of interesting HCI opportunities there. Okay, we got about 15 minutes left, so we're going to switch now and switch back to science, and we're going to view some ubiquitous technology as a new kind of scientific instrument, a telescope or a microscope. It's going to help us tackle some questions about how humans acquire speech. This project is called the Human Speechome Project, which was a riff on the earlier Human Genome Project, and we'll talk about why they chose this name in a moment. Okay, so in lecture 17, we looked at ubiquitous computing for studying social behavior. Lecture we just finished, we were thinking about trying to apply ubiquitous computing for monitoring health or physical, mental, and emotional well-being. Now we're going to switch and look at another, trying to infer or understand a third aspect of human behavior, the acquisition of language. Okay. The reading for this lecture comes from 2009 and is entitled New Horizons in the Study of Child Language Acquisition. Here are 3 different questions we could ask about how children acquire language. Big one, how do they learn language to begin with? We can break that down into a more specific and potentially testable hypothesis. What aspects of their physical and social environment influence how they pick up language? And what events in a child's past influence the learning of a language? Obviously, we can learn new languages as an adult. We are not tackling that in this lecture. Just children. They don't speak, they don't have language. How do they acquire it? Okay, so how is this usually studied? Usually studied by developmental psychologists. Developmental psychologists study adult development, the development from children into adults. Typical experiment would be to invite some children and their parents or caregivers into the lab and take a question like how do they learn language, and observe the children and the caregiver over a short period of time, a few minutes or hours in the lab in a controlled setting. we might see that in this control setting, we might see an interesting social dynamic emerge among the child and caregiver. Like, for example, the parent looks at an object, like the blue object here, repeatedly pronounces the name of that object, blue block, while we see from a video image and an audio from a video feed and an audio feed, we can infer the gaze of the parent. We can infer that they're looking at the object. A second or two later from the audio feed, we get the fact that they're saying the name of the object. We then observe that the child looks at the parent's eyes first and looks at the parent's eyes and immediately saccades. The child moves their eyes to focus on the same object that the parent is looking at. So again, this might seem very obvious to us, but thinking about thinking is misleading. Children and most of us, because we're social creatures, we can infer what someone else is looking at by looking at their eyes and performing some geometric transformation to move our eyes, not in the same way that the parents move their eyes, but in a particular way that we come to focus on the same object. So we might be able to infer that the child is using the information, the gaze direction of the parent, to move their eyes and now pay attention to or attend to the same object. And a second or two later in the audio feed, we hear the child say the same word that the parent did. Okay. And then asked, does the child remember the label for that object? Does the child remember what that object is called? If we show that child the object later, the child says the object's name. Assuming we saw all this in the lab, this raw data may suggest a particular hypothesis or a particular answer to the question of how children learn language. They do it through what's known as joint attention. And we'll talk more about joint attention when we talk about robots next week. Joint attention, as the name implies, is the parent is somehow trying to draw the child to attend to the same thing that the parent is. And with their joint or jointly focused attention, it's at that point that the parent can best supply some information or can best scaffold language acquisition in the child. That's a hypothesis. That's maybe how children acquire language. Maybe that's how they acquire some words but not others. Who knows? Okay. However, of course, we're doing this in the lab. So how natural is the interaction between a parent and a child in the lab? Is this the fact that, at least for the parent, and probably for the child as well, they're in a very unfamiliar setting that's going to alter their behavior, which might lead us off track. They may do things slightly differently or very differently from how they would do things at home. So in this experiment that we're going to look at today from Professor Deb Roy at MIT, he took a very different approach to studying how children learn language, which was, instead of bringing a child into the lab for a few minutes or hours, Professor Roy observed a single child continuously for the first 3 years of that child's life in the child's own environment. This is known as a longitudinal study because they were studying the child almost continuously over a long period of time. You can obviously guess what this child was. This child was Professor Roy's and his wife's own child. So it's a very interesting study, but it is also somewhat controversial because we have a scientist who is studying their own child. The child did not agree to be studied. So in all of psychology or human subject research in the United States, it is imperative you cannot carry out a scientific study unless you get signed consent from the subject. That's perfectly fine if the human subject is an adult, but what if the human subject is a child? If we want to study child behavior, the child can't sign for themselves. Who is able to sign on behalf of the child? The parent or the legal guardian. In this case, there's a conflict of interest because the person that wants to carry out the study and wants a signature is exactly the person who can provide the signature. Okay, so I usually put a disclaimer at this point in the lecture, which is if you do not agree with this particular study, not with its results, but how it was carried out, you're more than welcome to log off and skip over this lecture. Okay, otherwise, we've got 5 minutes left. So in the last 5 minutes, I'll play you the first 5 minutes of a TED Talk that was given by Deb, which summarizes this study. Next week, we'll dive back into the study and look at the HCI dimensions of this work.
Imagine if you could record your life. Everything you said, everything you did, available in a perfect memory store at your fingertips. So you could go back and find memorable moments and relive them, or sift through traces of time and discover patterns in your own life that previously had gone undiscovered. Well, that's exactly the journey that my family began 5.5 years ago. This is my wife and collaborator, Rupal, and on this day, at this moment, we walked into the house with our first child, our beautiful baby boy. And we walked into a house with a very special home video recording system.
Okay.
This moment and thousands of other moments special for us were captured in our home because in every room in the house, if you looked up, you'd see a camera and a microphone. And if you look down, you get this bird's eye view of the room. Here's our living room, the baby bedroom, kitchen, dining room, and the rest of the house. And all of these fed into a disk array that was designed for continuous capture. So here we are flying through a day in our home as we move from sunlit morning through incandescent evening, and finally lights out for the day. Over the course of 3 years, we recorded 8 to 10 hours a day, amassing roughly 250,000 hours of multi-track audio and video. So you're looking at a piece of what is by far the largest home video collection ever made. I think that's clear. And what this data represents for our family at a personal level, the impact has already been immense, and we're still learning its value. Countless moments of unsolicited, natural moments, not posed moments, are captured there, and we're starting to learn how to discover them and find them. But there's also a scientific reason that drove this project, which was to use this kind of natural longitudinal data to understand the process of how a child learns language, that child being my son. And so, with many privacy provisions put in place to protect everyone who's recorded in the data, we made elements of the data available to my trusted research team at MIT so we could start teasing apart patterns in this massive data set, trying to understand the influence of social environments on language acquisition. So we're looking here at one of the first things we started to do. This is my wife and I cooking breakfast in the kitchen. And as we move through space and through time, a very everyday pattern of life in the kitchen, in order to convert this opaque 90,000 hours of video into something we can start to see, we use motion analysis to pull out, as we move through space and through time, what we call space-time worms. And this has become a part of our toolkit for being able to look and see where the activities are in the data, and with it, trace the patterns of, in particular, where my son moved throughout the home, so that we could focus our transcription efforts, all the speech environment around my son, all the words that he heard from myself, my wife, our nanny, and over time, the words he began to produce. So with that technology and that data and the ability to, with machine assistance, transcribe speech, we've now transcribed well over 7 million words of our home transcripts. And with that, let me take you now for a first tour into the data. So you've all, I'm sure, seen time-lapse videos where a flower will blossom as you accelerate time. I'd like you to now experience the blossoming of a speech form. My son, soon after his first birthday, would say gaga to mean water. And over the course of the next half year, he slowly learned to approximate the proper adult form, water. So we're going to cruise through half a year in about 40 seconds. No video here, so you can focus on the sound, the acoustics of a new kind of trajectory. Gaga to water. He sure nailed it, didn't he?
Okay, I think we'll watch the rest of this next time. You have a quiz due tonight. You're working on deliverable 9. I wish you a good and safe rest of the week and weekend, and I'll see you next Tuesday. Thanks, everyone. Bye-bye.